Good afternoon everyone, my name is Leo D. Varnayha. I'm going to talk about types of energy. There are 5 different kinds of energy. First is mechanical, electromagnetic, electrical, chemical, and thermal. The next is what is mechanical energy. The mechanical energy due to object motion, kinetic or position potential. The example of mechanical energy, the blowing balls has mechanical energy. When the ball strike, the pen's mechanical energy is transferred to the pens. The next is example of mechanical energy. There are 3 types of mechanical energy. Like take a look at picture. Like a skating, swimming, and etc. Next, what is electromagnetic energy? Light's energy includes energy from gamma rays, X-ray, ultraviolet ray, visible lights, infrared rays, microwave, and radio band. Next is what is electrical energy? Energy caused by the movement of electrons, easily transported through power lines and converted into the other forms of gamma rays energy. Next is what is chemical energy? Energy that is available from release from chemical reaction. The example of the chemical energy, the chemical bonds is a mastic store energy that is transformed into thermal energy when the match is struck. The next is example of chemical energy. Like a cotton candy, battery, and carbon or uling, and etc. Next is what is thermal energy? Heat energy. The heat energy of an object determines how effective its atoms are. Excited, hot atom. The example of the thermal energy, a hot object is one whose atom and molecules are excited and whose rapid movement. Like a laid-back cold atom. A colder object's molecules and atoms will be shoeless.
Law of Thermodynamics. Thermodynamics is the study of the effects of work, heat, and energy on a system. Thermodynamics is only concerned with microscopic, large-scale change and observation. Getting started. All of thermodynamics can be expressed in terms of 4 quantities: temperature, internal energy, entropy, heat. Temperature is the measure of hotness or coldness expressed in terms of any of several scales, including Fahrenheit and Celsius. Temperature indicate the direction in which heat energy will spontaneously flow from a hotter body, one and a hotter temperature, to a cold body, one at a lower temperature. Internal energy. In thermodynamics, the property of state function that define the energy of a substance in the absence of effects to polarity and external electric, magnetic, and other field. Entropy is a scientific concept as well as a measurable physical property that is most commonly associated with a state of disorder, randomness, or uncertainty. Heat. Scientists define heat and thermal energy transfer between two systems and different temperatures that come in contact Heat is written with the symbol Q or Q and it as unit of joules. These quantities will be defined as we progress through the lesson. Classical versus statistical. Classical thermodynamics concern the relation between bulk properties of matter. Nothing is examined at the atomic or molecular level. Statistical. Thermodynamics seeks to explain those bulk properties in terms of constituent atoms. The statistical part treats the aggregation of atoms, not the behavior of any individual. Introduction. According to British scientist C. P. Snow, the three laws of thermodynamics can be humorously summarized as 1. You can't win. 2. You can't ever break even. 3. You can't get out of the game. You can't win because you can't not get any more energy of a system that you put in. You can break even because you can even get the same amount of energy out of a system that you put in. You can get out of the game because entropy is the universe is always increasing. 1.0 You can't win. First law. The first law of thermodynamics is an extension of the law of conservation of energy. The change in internal energy of a system is equal to heat added to the system minus the work done by the system. Second law of thermodynamics 2.0 You can break even. Second law. Think about what it means to not break even. Every effort you put forth, no matter how efficient you are, will have any tiny bit of waste. The second law can also be stated that heat flows spontaneously from a hot object to a cold object. First law of thermodynamics is generally thought to be the least demanding to grasp as it is an extension of the law of conservation of energy, meaning the energy can be neither created nor destroyed. However much energy there was at the start of the universe, there will be that amount at the end. The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. The entropy of a system at absolute zero is typically zero, and in all cases is determined only by the number of different ground state it has.
So, process of terminology. There are four processes of terminology. First is adiabatic, isothermal, isobaric, isochoric. So first is diabatic process. A diabatic process transfers no heat, negative, therefore Q equals to 0. Triangle U equals to Q negative W. So when a system expands adiabatically, W is positive. The system doesn't work. So triangle U is negative. So if the W is positive, which means this doesn't not work, it will result a negative process. So when a system compress adiabatically, W is negative, work is done on this system. So triangle U is positive. So if the W is negative, it means the process is good and it will result positive. The second process, isothermal process. An isothermal process is a constant temperature process. Any heat flow into or out of the system must be slow enough to maintain thermal equilibrium. For ideal gases, if triangle T is 0 and triangle U equals to 0, therefore Q equals to W is an energy entering the system of Q must leave as work W. So the energy entering the system of Q and end up with W. The third, isobaric process. The third process. An isobaric process is a constant pressure process. Triangle U equals W and Q are generally non-zero, but calculating the work done by an ideal gas is straightforward. W equals P dot triangle B. Water boiling in a saucepan is an example of an isobaric process. So the isobaric process, which mean this is ni siya gabukal na tubig, like anang mag-init og tubig. Kung magbukal na to siya, nay magawas nga aso. Mo to siya example sa isobaric process. The fourth one of process is isochoric process. Of an isochoric process is a constant volume process. When the volume of a system doesn't change, it will do not work on its surrounding. W is equal to 0. So the isochoric process ini siya constant volume process nga dili siya mausog. It doesn't change for any surroundings, like heating gas in a closed container. Dili mausog o dili pud siya makuhaan sa sulod sa container. Sa sulod sa container nga heating gas, muna siya example sa isochoric process. Heat capacity. So heat capacity is the amount of heat required to raise a certain mass of material by a certain temperature is called heat capacity. Q equals mc lower x triangle T. The constant C lower x is called the specific heat of substance of X. SI units of J slash Kj dot K. So the heat capacity is this amount of a required. These are temperature. So familiar na kayo tas temperature, no? So muna siya ang temperature nga mo base sa kung pila ang heat capacity sa any material or pwede po sa atong body. Muna siya mo compute of how much nga naa sa sulod sa material ang kainiton or sa atong body. Muna siya mo base heat capacity. That's all.
Good morning. My name is James Andrew Francisco, and this is my report about heat engine and engine efficiency. Heat engine. Heat engine is a device which transforms heat into work and is called a heat engine. This happens in a cyclic process. Heat engine requires a lot of hot reservoir to supply energy and a cold reservoir to take in the excess energy. The steam engine and the steam turbines are the two of the most well-known examples of a heat engine, and the invention of the steam engine was an important historical event in the industrialization of society. Cycles: the Otto cycle, the diesel cycle, and the Carnot cycle. Otto cycle is an idealized thermodynamic cycle that describes the functioning of a typical spark ignition piston engine. It is the thermodynamic cycle most commonly found in automobile engines. Diesel cycle. The diesel cycle is a combustion process of a reciprocating internal combustion engine. In it, fuel is ignited by heat generated during the compression of air in the combustion chamber, into which fuel is then injected. This is in contrast to igniting the fuel-air mixture with a spark plug as the Otto cycle engine. Carnot cycle. The Carnot cycle is the optimum cycle, and all cycles incline toward this optimum. Maximum adiabatic thermal efficiency is achieved by approaching the isothermal compression and expansion of the Carnot cycle, or by intercooling the compression and reheating the expansion process. Engine efficiency. Engine efficiency of thermal engines is the relationship between the total energy contained in the fuel and the amount of energy used to perform useful work. There are two classifications of thermal engines: internal combustion and external combustion engines.
2.5 engine efficiency. Thermal efficiency of heat engine is E equals 1 plus heat pump into cold reservoir over heat taken from cold. The engine statement of the second law. It is impossible for any system to have an efficiency of 100%. Other statement of the second law. It is impossible for any process to have as its sole result the transfer of heat from a cooler object to a warmer object. 2.6 Practical uses. Automobile engines, refrigerator and air conditioner all worked on the principle laid out by the second law of thermodynamics. Ever wonder why you can't cool your kitchen in the hot summer by leaving the refrigerator door open? Feel the air coming off the back you heat or the air outside, cool the air inside. See you can break even. 3.0 You can get out of third law. No system can reach absolute zero. This is one reason we use the Kelvin temperature scale. Not only is the internal energy proportional to temperature, but you never have to worry about dividing by zero in an equation. There is no formula associated with the third law of thermodynamics. Implication of third law. Might researcher achieved 450 picolbin in 2003. Molecules near this temperature have been called the fifth state of matter. Bose-Einstein conditionings assume things like superfluidity and superconductivity happen at this temperature, exciting frontier of research. The zeroth law, the first and second laws, were well entrenched when an additional law was recognized. It, if object A and B are each in thermal equilibrium with each other, allows us to define temperature relative to an stabilized standard. Object 1 is the thermometer, and the left bottom side of the thermometer is object 2, and the right bottom side of the thermometer is object 3. When two objects are separately in thermodynamic equilibrium with the third object, they are in equilibrium with each other object in thermodynamic equilibrium have the same temperature. 2.1 temperature in standard heat versus temperature heat and the thermometer are related and often confused. More heat usually means a higher temperature. Heat is energy that is transferred from one body to another as the result of a difference is temperature. The temperature is a measure of hotness or coldness expressed in terms of any of several arbitrary scales like Celsius and Fahrenheit. The symbol of temperature is T and its unit is Kelvin Celsius or Fahrenheit. Heat is energy transfer. Temperature is proportional to internal energy. Fahrenheit, Celsius, and Kelvin temp scales.